Hi guys, this is section 20.8, pardon me, on benzene. And benzene is our first introduction to a wider world of organic molecules. Up to this point, you've learned about straight chain alkanes, branch chain alkanes. You've even learned a little bit about alkenes and alkynes. But benzene is entirely different. Let's take a look at why. First of all, this ring right here is the benzene. This piece coming off is not part of the benzene. This ring right here is benzene. This piece, and this piece are not part of the benzene. Here is the benzene ring. This piece and this piece are not part of the benzene. And what I want you to take away from this slide is the idea that benzene is almost like a hub. Each one of these hydrogens on the benzene can be taken off and replaced with a new piece. Sometimes that new piece is very small, like right here. It's just an oxygen and a hydrogen. Sometimes the new piece is bigger, like all of this. But the idea is that a benzene molecule has 6 oxygens on it that can be pulled off and replaced with new things. And so the flexibility that benzene offers is just staggering. To put this another way, there are literally millions of molecules that incorporate benzene into their structure. Many of them are naturally occurring, many of them are artificial. People discovered the shape of benzene in about the middle of the 19th century, and that sort of started a revolution in what kinds of molecules chemists could work with. For example, it ushered in the era of the first artificial dyes. And today you can find these benzene rings in molecules that range in everything from artificial dyes to artificial colors to medicines to petrochemicals to synthetic narcotics. They're all over the place. We've even found benzene rings in space. I mean, they're truly ubiquitous. Here is how benzene usually gets represented. These are 3 ways. There are other ways you can do it, but these are the most common. So here's a ball and stick model. Of course, the black is carbon and the white is hydrogen. 6 carbon, 6 hydrogens. How about these dotted lines? Well, the dotted lines represent the dotted lines represent double bonds. But what happens is if you draw it out this way instead, every carbon has to make 4 bonds. And the way to get that to work in a ring is to alternate double bond, single bond, double bond, single bond. And if you do that, you can pick any carbon. Pick this one right here. It's got 4 bonds. 1, 2, 3, 4. Pick any other carbon. This one right here. 1, 2, 3, 4 bonds. Right? So how do you represent that? Let's think about what these bonds mean. This means there are 4 electrons shared here. Single bond means there are 2 electrons shared here. 4 electrons, 2 electrons, 4 electrons, 2 electrons, except that when chemists measure these bonds, you may recall from earlier in chapter 20, single bond should be a little bit longer, double bond should be a little bit shorter. That's not what they measure. They measure every single carbon-carbon bond as being halfway between a single bond. In other words, it's a little bit shorter than a single bond should be. It's a little bit longer than a double bond should be. It's like a 1.5 bond. So how do you write that? Well, these dotted lines are the way that chemists came up with writing that. And this is called resonance. The idea is that every one of these carbons has a bond with 2 electrons, and those 2 electrons stay there, right? But wherever there's a double bond, 2 of the electrons are stuck between the 2 carbons, but the other 2 electrons are not stuck. They're free to move around the ring. So we have 2 electrons here, 2 more electrons here, and 2 more electrons here. That's 6 electrons in total that are free to move around the ring. That's what this is representing. 6 electrons that can move around the ring. That's called resonance. One of the effects it has is to make benzene a very stable molecule. And that's one of the reasons that it's so ubiquitous, is it forms good, durable molecules. Pardon me. This is another way of writing benzene. You've got the hexagon, and then you just put the lines to represent the double bonds. Another way that people will often write this that I haven't included on this slide is a hexagon with a circle inside. So if you look at your notes, you'll find that hexagon with a circle inside, which also represents benzene. All three of these, plus the ones in your notes, are different ways to represent the exact same molecule. Here are a couple more molecules that are fairly complicated, but it just shows you that benzene can pop up in lots of places. Here's the benzene ring, and this is an acetate ion. If we were to stick one more hydrogen on here, it would become acetic acid or vinegar. So this means a piece of acetate has been stuck on to benzene, and what this acetate does is interesting. It allows this molecule to cross the blood-brain barrier. So we have acetate, and then everything left over, this piece right here, and the benzene ring, is called salicylic acid. So aceta for acetate, salicylic acid, acetylsalicylic acid. That's aspirin. Aspirin makes your headache go away because it can cross the blood-brain barrier. On the right side, we have another molecule. This molecule has two acetates, one right here and one right here. Again, these would be vinegar if we popped them off and stuck a hydrogen on them. And then it's got all of this stuff back here. So it's a little more complicated than aspirin, but you can see the benzene hiding right back there. Well, if one acetate makes crossing the blood-brain barrier possible, two acetates make it cross that much faster. This molecule has greater access to your brain than this molecule. The molecule on the left with one acetate is aspirin. The molecule on the right with two acetates is heroin. Other than the acetates, they're chemically quite similar, right? So in a certain sense, the difference between a molecule that helps you feel better and a molecule that's absolutely devastating is simply having access to your brain. And that access is provided by 1, 2, 3, 4, 5, 6, 7 atoms. 7 atoms are the difference between having your headache go away and having your life ruined. That's just staggering to me. So this is the section on benzene. There's more in the notes that you can find, but this is a pretty solid introduction. I guess I should make one final comment here. You'll notice the word aromatic compounds keeps popping up. That is because in the 19th century, when people were figuring out how benzene worked, they noticed that it was often associated with molecules that had smells, things like vanilla or cinnamon. And for that reason, they initially believed that benzene was always found in aromatic molecules. And so that's where the name comes from. Today, we've known for many, many decades that that's not the case, but you know how history is. Something gets started and it sticks. And so that's the language we use today.